for the final video for this unit, first I'm going to talk about Dalton and Henry's laws. So Dalton's laws state here that all partial pressures add up to the total pressure. So if we were to take the pressure of O2 and the pressure of CO2, just the pressure of nitrogen that's in the air, plus all of the things, it would equal P total, or these pressures equal the total pressure altogether. And then when we talk about Henry's law, we talk about how the more soluble a gas is, the less pressure is required to move it or to push it. So that means that solubility is inverse to pressure. So the more soluble is less pressure. And that's important when we talk about CO2 and O2. It takes, we take the solubility of each, and if we put in the same pressure, or if we look at their solubilities, then it takes 160 millimeters of mercury for O2, but only 40 for CO2. And that's because their solubilities are different. CO2 is much more soluble, which means that we don't need as much pressure to move it. Next, we're going to talk about the alveolar gas equation, which I've set up here. And then we're going to talk about all of its parts and why we use each of those. So this is that gas equation. So it's set up as 0.21 times the concentration of the atmospheric pressure and the pressure of water, vapor, minus the pressure of CO2 divided by R. So 0.21 is the partial pressure of oxygen in the air. PATM is the pressure of atmosphere, and the total pressure of the atmosphere, which is 760 millimeters of mercury. pH2O is a calculated value of the water vapor pressure in your lungs. This R is the respiratory quotient, which is generally calculated to be 0.85. And they calculate that by taking the pressure of CO2 divided by the pressure of O2. So it's a very valuable number in a clinical setting, but we round it to 0.85 on average. And then this numerator is the pressure of CO2 in blood, which is typically 40. And that all equals the pressure of oxygen in the alveolus. So the next thing that I want to talk about is the ventilation and perfusion ratios. And I'll give you a few examples of what might cause these ratios to change. So we call them VQ ratios. V is representative of the air and Q is of the blood. So right here at the hilum of the lung, we have a VQ that is considered normal, it's average. When we move into the inferior lobe of this lung, then we say that there's less air and more blood. And so that's got a thrown off VQ ratio. And then this superior portion of the lung has a higher air to lower blood volume. So it's got another different VQ ratio. Here are a few of the things that could cause these ratios to change. So first I have a pulmonary embolism. That would increase the VQ ratio. I have a right-sided heart failure, which would also increase. And then my two that decrease, I have bronchitis and pneumonia. And so these are each kind of typical clinical things that we see, and we can kind of start to see if the VQ ratio is high. Could be a pulmonary embolism, could have right-sided heart failure, or the opposite if it's bronchitis or pneumonia. But that would be everything for this first part. In part 2 of this last essay, I'm going to talk about the total pulmonary and alveolar ventilation rate and why the slow and deep breathing is more beneficial than shallow breathing. So we'll use this equation to talk about the rate. So I have it here. So TV is the tidal volume of your lung. MV is the minute volume. Alveolar volume is this AV. BR is the breathing rate. And then F is the partial pressure of oxygen in your alveolus. So I have here a diagram of, this is your trachea coming down and then branching into your lung. So I also forgot to, color these in. This is orange and this is purple. So here, going down your whole trachea, and even these very beginning of these tertia bronchi, you have dead space. There's no gas exchange that happens here. Oxygen is coming in and it's all present, but there's no exchange of the gas here. Here in these green sections, we have the anatomical sections, and these never participate in gas exchange as well. This orange section is the physiological section, and it used to participate in gas exchange, but now does not. And then finally, we have the alveolar area. The alveoli that are incapable of gas exchange at the current time. Let me say that better. They're now incapable of doing it. Once they participate, it needs to reset before it can do it again. And it's this last section there. That is pretty simply how it works for the for the pulmonary and alveolar ventilation rate. Slow breathing will increase the alveolar ventilation, so will increase the capability of these things working. And so when you decrease your, when you speed up your breathing, and you take shallow breaths, not as much oxygen is coming in, and so your CO2 isn't being replaced. So your CO2 will actually start to increase, which will not allow you to get as much oxygen through, and so you will have a harder time breathing. In the final part of this final video, I'm going to talk about the difference between restrictive and obstructive pulmonary diseases. So I'll start in this restrictive one. So we lose compliance of our lung, which increases the elastance. And because of this, we lack inflation of our lung, which means no air in. We have a huge decrease of air in, which is not good. Versus in the obstructive disorders, we actually have an increase in the compliance, and so our elastance goes down. We have two types of this. They can come from, first, emphysema, which is some characteristics are you have forced expiration, you'll have pursed lips, and you also have a barrel chest, or from bronchitis. And in bronchitis, it actually takes more force to expire air, and you'll have poor venous return, and so you might actually appear slightly blue. And when you trap the air from emphysema, you'll start to have alveolar destruction. This happens when the secondary bronchi in your lungs start collapsing and they trap the air inside. And you start to get this thing called the Boulez formation, which is the coverage of infected alveoli, and they can then no longer participate in gas exchange. And so emphysema is very dangerous because you'll basically lose the ability to exchange CO2 for oxygen and keep your body healthy.